Introduction. Let yourself settle into this moment. Find that space where your body can truly rest, where the gentle weight of the day begins to lift from your shoulders like morning mist rising from a quiet lake. Take a slow breath, feeling the air move through you, and as you exhale, let any lingering tension dissolve into the darkness around you. You don't need to do anything right now except listen, and even that requires no effort at all. Just let the words wash over you like waves lapping at a distant shore. Before we drift into tonight's journey through the cosmos, I want to thank you for being here. If you're finding comfort in these explorations, if the marriage of science and relaxation speaks to something in you, consider subscribing to the Science Pillow. And if a particular phrase or idea resonates tonight, a gentle tap on the like button helps others discover this oasis of curiosity and calm. But these are merely invitations, not obligations. Your presence here is gift. Enough. Tonight, we're going to explore one of the deepest mysteries in all of physics, a place where our best theories break down and the universe whispers that there's something we don't yet understand. We're going to talk about black holes, those enigmatic shadows in the fabric of spacetime, and about something that might not actually exist at their hearts. The singularity, that point of infinite density where the laws of physics supposedly crumble into mathematical chaos, may be nothing more than a sign that we're asking the wrong questions. So breathe deeply, let your mind wander where it will, and join me as we venture into the darkness to find, perhaps, a different kind of light. The promise and the problem. Close your eyes for a moment and imagine the darkest thing you can conceive. Not merely the absence of light, but a region of space where light itself cannot escape, where the very fabric of reality warps and twists into shapes that defy everyday intuition. This is a black hole, one of the most extreme objects that physics predicts can exist in our universe. For decades, they remained theoretical curiosities, mathematical oddities lurking in Einstein's equations. But now we know they're real. We've detected the gravitational waves from colliding black holes. We've photographed the glowing ring of superheated gas swirling around the supermassive black hole at the center of the M87 galaxy, that orange donut of light surrounding a shadow darker than anything in our experience. Black holes are real. Of this, there is no doubt. They form when massive stars, many times heavier than our Sun, exhaust their nuclear fuel and can no longer resist the crushing weight of their own gravity. The star collapses, compressing more and more matter into less and less space, until something extraordinary happens. At a particular radius, a boundary forms in spacetime itself. This is the event horizon, an invisible one-way membrane that marks the point of no return. Anything that crosses this threshold, whether a particle of dust or a beam of light or an unfortunate astronaut, will inexorably fall inward. There is no escape, no turning back. The event horizon isn't made of anything physical. It's not a wall or a surface you could touch. It's a geometric property of spacetime itself, a place where the warping of reality becomes so extreme that all paths lead inward. For a non-rotating black hole, this boundary sits at what we call the Schwarzschild radius, named after Karl Schwarzschild, a German physicist who derived the first exact solution to Einstein's field equations while serving on the Eastern Front during World War I. The formula is elegant in its simplicity. The Schwarzschild radius depends only on the mass of the black hole, nothing else. Double the mass, double the radius. For an object with the mass of our Sun, the Schwarzschild radius would be about 3 kilometers. That means if you could somehow compress the entire sun down to a sphere just 6 kilometers across, smaller than many cities, it would become a black hole. For Earth, the Schwarzschild radius is a mere 9 millimeters, about the size of a grape. Of course, neither Earth nor the Sun will ever collapse into black holes. They lack the necessary mass, and there are physical forces that prevent such a collapse. But the point remains. Any amount of mass, if compressed into a small enough volume, will create an event horizon. And beyond that horizon, according to general relativity, lies something deeply troubling. Einstein's theory of gravity, general relativity, is one of humanity's crowning intellectual achievements. It reimagines gravity not as a force in the traditional sense, but as a consequence of how mass and energy curve the geometry of spacetime itself. Imagine spacetime as a flexible fabric, like a rubber sheet stretched taut. Place a heavy ball on the sheet, and it creates a depression, a curvature in the fabric. Other objects rolling nearby will curve their paths, falling toward the depression. That's how planets orbit stars, how light bends around massive objects, how the universe itself expands and evolves. General relativity has passed every experimental test we've thrown at it. It predicted the bending of starlight around the sun, confirmed during a solar eclipse in 1919. It predicted gravitational time dilation, the fact that time runs slower in stronger gravitational fields, a phenomenon we must account for in GPS satellites orbiting Earth. It predicted gravitational waves, ripples in spacetime itself, which we detected for the first time in 2015 when two black holes spiraled together and merged. The theory is spectacularly successful, and yet, when we apply it to the interior of a black hole, it tells us something that should make us deeply uncomfortable. According to the equations of general relativity, once matter collapses past the event horizon, nothing can stop it from continuing to fall inward. There are no forces strong enough to resist gravity at these extremes. The matter compresses further and further, the density rising without limit, until all the mass of the black hole arrives at a single point. Not a very small point, but a point of literally zero size, zero volume, infinite density. This is the singularity, the mathematical endpoint predicted by the equations. At the singularity, the curvature of spacetime becomes infinite. Physical quantities like density and gravitational field strength diverge to infinity. And when physicists encounter infinities in their theories, it's almost always a sign that something has gone wrong. Think about it. Infinite density means infinite mass packed into zero volume. Infinite curvature means spacetime is torn apart, ceasing to have any meaningful structure. At such a point, the equations of general relativity literally cannot tell us what happens next. They break down completely. Input the conditions at the singularity into Einstein's field equations, and you get nonsensical answers, mathematical expressions that blow up or become undefined. The theory, for all its elegance and predictive power, reaches a boundary beyond which it cannot see. For decades, physicists hoped that singularities might be mere mathematical artifacts, peculiarities that arose only in idealized, perfectly symmetric situations. Perhaps, they thought, in a more realistic collapse with imperfect symmetry, with rotation and turbulence and all the messy details of actual astrophysical processes, the singularity would be avoided. Perhaps the matter would somehow bounce back, or be held up by some unknown force, or behave in a way that kept everything finite and well-defined. Then, in 1965, a British physicist named Roger Penrose proved that this hope was misplaced. Penrose showed, through an elegant mathematical argument, that singularities are unavoidable in black holes. His singularity theorem demonstrated that once a trapped surface forms, a region where even outgoing light rays are pulled inward, the formation of a singularity becomes inevitable. It doesn't matter if the collapse is perfectly symmetric or wildly chaotic. It doesn't matter what the collapsing matter is made of. Given reasonable assumptions about the energy content of the universe, singularities must form. For this work, along with his other contributions to our understanding of black holes, Penrose was awarded half of the 2020 Nobel Prize in Physics. Penrose's theorem was both a triumph and a problem. A triumph because it showed that black holes, far from being fragile mathematical constructs, are robust predictions of general relativity. They form generically under realistic conditions. This put to rest the notion that black holes were mere theoretical curiosities. But it was also a problem because it meant that general relativity predicts its own breakdown. The theory tells us that under certain circumstances, which occur naturally in our universe, we will encounter conditions where the theory itself ceases to function. It's as if the equations come with a built-in self-destruct mechanism. Now, you might be thinking, so what? The singularity is hidden behind an event horizon. We can never see it, never directly observe it. Maybe it's acceptable for our theories to break down in regions we can never access. This idea has a name: cosmic censorship. The hypothesis suggests that nature always hides singularities behind event horizons, protecting the rest of the universe from their pathological properties. And, for the most part, this seems to be true. The singularities that form from stellar collapse are, indeed, cloaked by event horizons. We call these black holes. But the existence of hidden infinities should still trouble us. Physics is supposed to be a complete description of nature. If our best theory of gravity says that certain configurations lead to infinite quantities and mathematical breakdowns, it strongly suggests that we're missing something important. Moreover, there's another singularity in general relativity that isn't hidden at all: the Big Bang. If we run the expansion of the universe backward in time, general relativity tells us that all the matter and energy in the cosmos was once compressed into a point of infinite density. This cosmological singularity sits in our past, and it's not protected by any event horizon. It's part of the observable universe's history. The singularities predicted by general relativity, both the ones lurking inside black holes and the one at the beginning of time, are trying to tell us something. Their flags waving in the mathematical landscape, marking places where our understanding is incomplete. And, increasingly, physicists believe they know what's missing: quantum mechanics. General relativity is a classical theory. It treats spacetime as a smooth, continuous fabric. It doesn't account for the quantum nature of reality, the fundamental granularity and uncertainty that governs the behavior of matter and energy at the smallest scales. For most situations, this is fine. Quantum effects are typically only important for tiny objects like atoms and subatomic particles. The orbits of planets and the bending of light around galaxies can be understood perfectly well without invoking quantum mechanics. But at a singularity, we're compressing enormous amounts of mass into infinitesimally small regions. We're reaching down to scales where quantum mechanics should matter enormously. And when we try to apply quantum mechanics to gravity, or gravity to quantum systems, we encounter deep conceptual and mathematical problems. The uncomfortable truth is that general relativity and quantum mechanics, our two most successful physical theories, don't play well together. They rest on fundamentally different assumptions about how nature works. Quantum mechanics assumes a fixed background of space and time against which particles and fields evolve. General relativity says that space and time are dynamical, shaped by matter and energy. Reconciling these perspectives requires a theory of quantum gravity, a framework that treats gravity quantum mechanically and spacetime as emerging from some more fundamental description. We don't have a complete, experimentally verified theory of quantum gravity yet. String theory, loop quantum gravity, and other approaches are works in progress, each with its own strengths and unresolved challenges. But there's a growing consensus among physicists that whatever the correct theory turns out to be, it will resolve the singularities. The infinities will vanish. And when we look at the center of a black hole through the lens of quantum gravity, we'll find something finite, something well-defined, something that obeys coherent physical laws. The singularity, in other words, is almost certainly not real. It's a mirage, an artifact of applying general relativity beyond its domain of validity. The black hole is real, but the singularity at its heart is not. Understanding black holes. The observable facts. Let's step back for a moment from the exotic mathematics and ground ourselves in what we actually observe, what we know with confidence about these mysterious objects lurking in the darkness of space. Sometimes, when we venture into the deep waters of theoretical physics, it helps to return periodically to shore, to touch the solid ground of empirical fact. Black holes, as observational entities, remained elusive for most of the 20th century. John Michell, an English clergyman and natural philosopher, speculated about them as far back as 1784, imagining stars so massive that their escape velocity would exceed the speed of light. But these were thought experiments, mathematical exercises. No one knew if such objects could actually exist in nature. Even Einstein, whose equations predicted black holes, was skeptical that they would ever form. The idea seemed too strange, too extreme. That began to change in the 1960s. Astronomers discovered quasars, extraordinarily bright objects at immense distances that emitted more energy than entire galaxies. The only explanation that made sense was matter falling into supermassive black holes, converting gravitational potential energy into radiation with stunning efficiency. Then came the discovery of X-ray binary systems, pairs of stars where one member was invisible, yet clearly very massive and compact, pulling material from its companion. The matter spiraling inward would heat up to millions of degrees, emitting X-rays before vanishing past the event horizon. Cygnus X1, discovered in 1964, became one of the first strong candidates for a stellar mass black hole. As observational techniques improved, the evidence mounted. We tracked stars in the center of our own Milky Way galaxy, watching them swing around an invisible object in orbits that revealed its mass. About 4 million times the mass of the Sun, packed into a region smaller than the orbit of Mercury. This is Sagittarius A star, the supermassive black hole at the heart of our galaxy. We've now found supermassive black holes, millions to billions of solar masses, at the centers of most large galaxies. They're not rare oddities, they're a standard component of galactic architecture. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from two stellar mass black holes spiraling together and merging. This was a watershed moment. For the first time, we could hear black holes through the ripples they create in spacetime itself. Since then, LIGO and its European counterpart Virgo have detected dozens of such events. We can measure the masses of the merging black holes, their spins, the energy released in gravitational waves. The observations match the predictions of general relativity with breathtaking precision. Then, in 2019, the Event Horizon Telescope collaboration released the ENIG, first direct image of a black hole's event horizon. Or rather, they imaged the shadow of the event horizon, surrounded by a glowing ring of hot gas. The target was a supermassive black hole at the center of the galaxy M87, about 55 million light-years away, with a mass of about 6.5 billion suns. The image showed exactly what general relativity predicted: a dark circle, the shadow cast by the event horizon against the bright backdrop of the accretion disk. In 2022, they released an image of Sagittarius A star, our own galactic center black hole, confirming the presence of its shadow as well. These observations tell us that black holes exist, and that their large-scale properties, their event horizons, and the spacetime around them match the predictions of general relativity remarkably well. The event horizon is real. The warping of light around the black hole is real. The way matter behaves as it approaches the event horizon is real and matches our mathematical models. General relativity describes the exterior of black holes with extraordinary fidelity. But here's the crucial point. Everything we have observed concerns the outside of black holes. The event horizon is a one-way boundary. Information cannot flow from the interior to the exterior. Anything that crosses the horizon is lost to us forever. We cannot see what happens inside. We cannot probe the interior directly. All our observations, no matter how sophisticated, can only tell us about the region outside the event horizon and the event horizon itself. The singularity, if it exists, sits deep inside, forever hidden from view. So, when we talk about what's inside a black hole, we're not speaking from direct observation. We're extrapolating, using our theories to project what we think should happen based on what we know about physics. And this is where the trouble begins. From the perspective of someone far away from a black hole, watching matter fall in, something very strange happens. As an object approaches the event horizon, general relativity predicts that time dilation becomes extreme. Clocks near the horizon run slower and slower relative to distant clocks. To a faraway observer, it appears that in-falling matter takes an infinite amount of time to actually reach the event horizon. The light from the falling object becomes increasingly redshifted, stretched to longer and longer wavelengths, fading toward invisibility. It's as if the object freezes at the horizon, never quite crossing it from the outside observer's perspective. But from the perspective of someone falling into the black hole, the experience is entirely different. They would cross the event horizon in a finite amount of their own time, perhaps without even noticing anything special happening at that moment. There's no physical barrier at the horizon, no wall or surface. It's just a point in space-time with a particular geometric property. Once across, however, their fate is sealed. Inside the event horizon, all time-like paths, all possible futures, lead toward the center. Moving away from the singularity becomes as impossible as moving backward in time. The geometry of space-time itself compels you inward. For a stellar mass black hole, the tidal forces near the horizon would be catastrophic. Tidal forces arise because gravity is stronger closer to the black hole's center and weaker farther away. An object falling in feet first would experience much stronger gravitational pull on their feet than on their head. This differential force, the tidal force, would stretch the object like taffy, a process poetically called spaghettification. For a black hole of a few solar masses, the tidal forces at the event horizon would be strong enough to tear apart any known material, ripping atoms from molecules and shredding even atomic nuclei into their constituent protons and neutrons. For a supermassive black hole, however, the situation is different. The event horizon of a billion solar mass black hole sits so far from the center that the tidal forces there are actually quite gentle. An astronaut could, in principle, cross the horizon without being torn apart. They might not even realize they'd crossed the point of no return. Only later, as they fell deeper into the increasingly strong gravitational field near the center, would the tidal forces become lethal. What happens at the center, at the singularity itself? General relativity says the tidal forces become infinite. Anything approaching the singularity would be stretched infinitely in one direction and compressed infinitely in the others, crushed and torn beyond any possibility of description. Space-time curvature diverges to infinity. All physical quantities blow up. The equations break down completely. But should we believe this prediction? Should we trust general relativity all the way to the singularity? Physicists have a general principle. A theory is trustworthy only within its regime of validity. Newtonian mechanics works beautifully for everyday objects moving at everyday speeds, but it fails for objects moving near the speed of light or in very strong gravitational fields. Special relativity extends the range of validity to high speeds in flat spacetime. General relativity extends it further to strong gravitational fields and curved spacetime. But even general relativity must have limits. We know that general relativity is a classical theory, one that doesn't account for quantum mechanics. And we know that quantum effects become important at very small scales, typically around the Planck length, about 10 to the minus 35 meters. This is an unimaginably tiny distance, about 1,000,000,000,000,000 times smaller than an atomic nucleus. At the Planck length, the quantum fluctuations of spacetime itself become significant. The smooth fabric that general relativity assumes no longer holds. Spacetime becomes grainy, foamy, uncertain. The singularity, with its infinite density and curvature, represents an extrapolation of general relativity into a regime where the theory should not be trusted. It's like trying to use Newtonian mechanics to describe the interior of an atom. The theory simply isn't designed for that purpose. When we apply general relativity to the approach toward a singularity, we're pushing the theory beyond its breaking point. And the appearance of infinities is the theory's way of telling us that we've gone too far. The black hole is real. The event horizon is real. The warping of spacetime around the black hole is real. But the singularity, that point of infinite density at the center, is almost certainly an artifact of using the wrong theoretical framework. It's a placeholder, a mathematical expression of our ignorance. To understand what truly lies at the heart of a black hole, we need a theory that unites general relativity and quantum mechanics. We need quantum gravity, the Singularity Prediction. Let's slow down for a moment and really understand what general relativity tells us about singularities and why they're such a profound problem for physics. This is a place where the mathematics becomes insistent, where the equations speak with a clarity that cannot be ignored, even if what they're saying disturbs us. Roger Penrose's singularity theorem, published in 1965, was a landmark achievement. Before Penrose, many physicists suspected that singularities in black hole solutions might be artifacts of excessive symmetry. The earliest black hole solution, found by Carl Schwarzschild, assumed perfect spherical symmetry. Perhaps, people thought, if you allowed for rotation, or if the matter collapsed in a less orderly fashion, the singularity would be avoided. Maybe the matter would somehow miss the center, or quantum pressure would halt the collapse before reaching infinite density. Penrose showed that these hopes were unfounded. His theorem, elegant and rigorous, demonstrated that singularities are generic features of gravitational collapse. The key insight involved what he called trapped surfaces. Imagine a spherical surface in space. Normally, if you send out light rays from this surface, half of them will propagate outward, away from the center, and half will propagate inward. But near a black hole, in a sufficiently strong gravitational field, you can have a surface where even the outward-directed light rays are pulled back inward. This is a trapped surface. Once such a surface forms, Penrose proved that a singularity must develop. The geometry of space-time inside the trapped surface evolves in such a way that all matter within it is inexorably crushed to a point of infinite density. The assumptions of the theorem are physically reasonable. It requires that matter has positive energy density, which is true for all known forms of matter. It requires that gravity is attractive, which it is. It requires that the equations of general relativity hold. Given these modest assumptions, the existence of a trapped surface guarantees the formation of a singularity. And trapped surfaces form naturally when massive stars collapse. There's no escaping the conclusion. General relativity predicts singularities inside black holes. Stephen Hawking, who was Penrose's contemporary and collaborator, extended these ideas. Working with Penrose, Hawking proved theorems showing that singularities also exist in cosmology. If you run the expansion of the universe backward in time, you reach a state of infinite density and curvature at the Big Bang. The singularity at the beginning of time is just as inevitable, under the assumptions of general relativity, as the singularities inside black holes. But what exactly is a singularity in general relativity? The term is used somewhat loosely, and it's worth being precise. Mathematically, a singularity is a place where geodesics, the paths that free-falling objects follow through space-time, cannot be extended. Imagine falling into a black hole. Your trajectory through space-time is a geodesic. According to general relativity, if a singularity exists, your geodesic will reach a point where it simply ends. There's no continuation, no next moment. It's not that you hit something or transition to a different region. The geodesic terminates. Time itself, at least as measured along your path, comes to an end. This is deeply strange. In classical physics, we expect that if we know the state of a system at one moment, we can predict its state at all future moments. The laws of physics are deterministic, but a singularity represents a breakdown of determinism. We cannot predict what happens to matter that reaches a singularity because the very concept of what happens next loses meaning. The future simply doesn't exist beyond that point. Another way to characterize singularities is through curvature and variance. These are quantities constructed from the curvature of spacetime that don't depend on your choice of coordinate system. In flat spacetime, far from any gravitating bodies, these curvature invariants are zero. Near a star or planet, they're small but non-zero. As you approach a black hole's event horizon, they grow larger. And at a singularity, at least as predicted by classical general relativity, they diverge to infinity. The Kretschmann scalar, one such curvature invariant, is a measure of how severely spacetime is bent. At a Schwarzschild singularity, the Kretschmann scalar goes to infinity, indicating infinite curvature. Now, infinities are troublesome in physics. When you encounter an infinity in a calculation, it usually means one of two things. Either you've made a mistake, or your theory is inapplicable to the situation at hand. In the early days of quantum field theory, physicists encountered infinities when they tried to calculate certain processes, like the interaction between electrons and photons. These infinities plagued the theory and seemed to render it useless. Eventually, a technique called renormalization was developed, a systematic way to absorb the infinities into the definition of physical constants like the electron's mass and charge. After renormalization, the theory gave finite, testable predictions that matched experiments exquisitely well. But the infinities at gravitational singularities are different. They're not artifacts of a calculational procedure that can be removed by a clever mathematical trick. They represent places where the physical quantities described by the theory become infinite. Infinite density, infinite curvature, infinite tidal forces. And unlike the infinities in quantum field theory, there's no known renormalization procedure for singularities in general relativity. They seem to be intrinsic to the theory. This has led most physicists to conclude that the singularities predicted by general relativity are not real physical objects. Instead, they're signposts marking the boundaries of general relativity's domain of validity. When the theory predicts a singularity, it's admitting that it can no longer describe what's happening. It's reached the edge of its applicability. The situation is analogous to what happens in classical thermodynamics. In the 19th century, physicists developed beautiful theories to describe how gases behave, how temperature and pressure and volume relate to each other. But when you push these theories to extreme limits, such as cooling a gas to absolute zero temperature, the equations predicted strange things, like infinite densities or negative pressures. Of course, we now know that absolute zero is not actually reachable, and that quantum mechanics takes over before you get there, changing the behavior of matter in ways that classical thermodynamics didn't account for. The infinities in the classical theory were signals that quantum effects needed to be included. Similarly, the singularities in general relativity are signals that quantum effects, which the theory neglects, become crucial. General relativity is a classical theory. It treats spacetime as a smooth, continuous manifold. It doesn't account for the fact that at very small scales, quantum fluctuations should cause spacetime itself to become uncertain, granular, subject to the Heisenberg uncertainty principle. When you compress matter to densities where the Planck scale becomes relevant, quantum gravity effects should dominate, and quantum gravity, whatever its final form, is expected to prevent true singularities from forming. But we don't yet have a complete, experimentally verified theory of quantum gravity. String theory, loop quantum gravity, and other approaches each offer tantalizing clues, but remain works in progress. So we can't definitively say what replaces the singularity. We can't point to a specific equation and say, this is what's really happening at the center of a black hole. We can only argue, on general grounds, that the singularity is unlikely to be the final answer. It's worth emphasizing just how radical the singularity prediction is. Infinite density means cramming a finite amount of mass into zero volume. Zero volume means a point in the strict mathematical sense, a location with no spatial extent whatsoever. This isn't just very small, it's genuinely zero-dimensional. And at such a point, all the matter that fell into the black hole throughout its history would be concentrated. For a stellar mass black hole, that's several times the mass of the Sun, all at a single point. For a supermassive black hole, it could be billions of solar masses at a point. The implications are bizarre. In quantum mechanics, there's a fundamental limit to how precisely you can know both the position and momentum of a particle. This is the Heisenberg uncertainty principle. If you try to localize a particle to an infinitely small region, its momentum uncertainty becomes infinite, meaning it could have arbitrarily high energy. Particles with very high energy can create a particle-antiparticle pairs, more particles out of the vacuum. The attempt to squeeze something into a point necessarily creates a seething foam of quantum activity. The very notion of a point-like object with definite properties becomes questionable. Moreover, general relativity itself gives us hints that something is wrong at the singularity. Inside a black hole, the nature of space and time undergoes a strange transformation. Outside the event horizon, the radial coordinate is space-like, meaning you can choose to move outward or inward, just as you can choose to move left or right. The time coordinate is time-like, meaning time flows inexorably forward, and you can't choose to go backward. But inside the event horizon, these roles reverse. The radial coordinate becomes time-like, meaning you must move inward toward the center, as inevitably as you must move forward in time outside. And the time coordinate becomes space-like, meaning the singularity is not a place in space but a moment in time, a future moment that every observer inside the horizon is destined to reach. So the singularity is a moment in time, a moment when time itself ends. This is conceptually very different from a place in space, and it raises profound questions. If time ends, what does that even mean? Can time have an end? In our everyday experience, time is seamless, continuous. Moments follow one another in an unbroken chain. The idea that this chain could simply terminate, that there could be a last moment with no subsequent moment, is deeply counterintuitive. Yet this is what general relativity, taken at face value, tells us. Inside a black hole, you fall inexorably toward a future moment where time ends, where the curvature of spacetime becomes infinite, where you and everything else is crushed out of existence. It's a disturbing picture, and it's a picture that almost no physicists believe is accurate. The singularity, they suspect, is a fiction. It's what general relativity predicts when you use the theory beyond its limits. It's a mathematical artifact, not a physical reality. But if the singularity isn't real, what is there instead? Why infinities signal a problem? Let's take a moment to understand why physicists react with such discomfort when their equations produce infinities. This isn't mere mathematical fastidiousness or an aesthetic preference for finite numbers. The appearance of infinities in a physical theory is a profound red flag, a signal that something fundamental has gone wrong, or that the theory has been pushed into a regime where it no longer applies. In the history of physics, infinities have repeatedly appeared when theories were incomplete or incorrectly formulated, and their resolution has often led to deep new insights. Consider the ultraviolet catastrophe in classical physics. In the late 19th century, physicists tried to calculate the spectrum of radiation emitted by a hot object, what we call black body radiation. Classical statistical mechanics predicted that an ideal hot object should emit infinite amounts of energy at high frequencies, in the ultraviolet and beyond. This was absurd. Real objects clearly don't emit infinite energy. The prediction was wrong, and its wrongness pointed to a gap in classical physics. The resolution came with Max Planck's introduction of quantized energy levels, the beginning of quantum mechanics. The infinity disappeared once the correct framework was applied. Similarly, in the early development of quantum electrodynamics, the theory of how light and matter interact, physicists encountered infinities when they tried to calculate certain quantities, like the electron's self-energy. An electron creates an electromagnetic field, and this field contains energy. According to the theory, the electron should interact with its own field, and this self-interaction contributes to the electron's mass. But when you calculated this contribution, the answer came out infinite. For years, this seemed like a fatal flaw. Eventually, physicists developed the technique of renormalization, a way to systematically handle these infinities by absorbing them into the definitions of measurable quantities like mass and charge. After renormalization, the theory gave finite, incredibly accurate predictions. But even here, the initial appearance of infinities signaled that the theory, in its naive formulation, was incomplete. It needed renormalization to become a fully consistent framework. The infinities at gravitational singularities are different. They're not calculational artifacts that can be renormalized away. They represent the theory itself predicting that physical quantities become infinite. Quantities like density, curvature, and tidal force. And when a theory predicts that a measurable quantity becomes infinite, it's essentially throwing up its hands and saying, I don't know what's happening here. Think about what infinite density means physically. Density is mass per unit volume. Infinite density means you're dividing a finite mass by zero volume. But zero volume is not a physical concept in the way that small volume is. You can have a region of space a nanometer across. You can have a region a Planck length across, about 10 to the minus 35 meters. But zero volume means no region at all, just a point in the mathematical sense. And at a point, concepts like density become ill-defined. How do you measure the density of a point? What does it mean to say something occupies no space? Infinite curvature is similarly problematic. Curvature in general relativity describes how spacetime is bent. A flat sheet of paper has zero curvature. The surface of a sphere has constant positive curvature. A saddle shape has negative curvature. These are all finite values. Infinite curvature means spacetime is bent infinitely sharply, which is not a geometric configuration that makes sense in the usual framework of differential geometry, the mathematics underlying general relativity. One way to think about infinities is that they often arise when you take a limiting process too far, beyond where it should physically apply. Imagine compressing matter to higher and higher densities. As the density increases, general relativity predicts stronger and stronger gravitational fields. This is fine and matches observations up to a point. But if you keep compressing, ignoring all other physical effects, Eventually, you reach densities where quantum mechanics becomes important. Quantum mechanics introduces a kind of resistance to compression. The uncertainty principle means that confining particles to a small region gives them high momentum uncertainty, which translates to high kinetic energy. This energy provides a pressure that resists further compression. It's why white dwarfs, the remnants of sun-like stars, don't collapse further. The degeneracy pressure from electrons, a quantum mechanical effect, holds them up. Similarly, neutron stars are supported by the degeneracy pressure of neutrons. But in a sufficiently massive stellar collapse, even these quantum pressures are overwhelmed by gravity. The neutron star exceeds a critical mass, about 3 solar masses, and collapses into a black hole. General relativity then says the collapse continues all the way to a point. But this conclusion is reached by ignoring quantum effects on the structure of spacetime itself. We're treating spacetime as a classical, smooth background, while the matter becomes quantum. But if quantum mechanics is fundamental, and if gravity is part of nature, then at some point, spacetime itself must exhibit quantum behavior. It can't remain classical all the way down to zero size. The Planck scale is where we expect quantum gravity effects to become significant. At distances around the Planck length, times around the Planck time, which is about 10 to the minus 43 seconds, and energies around the Planck energy, the quantum fluctuations of the gravitational field become comparable to the gravitational field itself. Spacetime stops being a smooth fabric and becomes a roiling quantum foam, a seething sea of virtual particles, fluctuating metrics, and temporary geometries popping in and out of existence. In this regime, the classical description of spacetime breaks down entirely. General relativity, being a classical theory, cannot describe this regime. It has no mechanism for handling quantum fluctuations of the metric. So, when general relativity predicts a singularity, a region of infinite curvature, what it's really saying is, I've reached a point where the curvature is so extreme that quantum effects dominate, and I can no longer provide a reliable description. The infinity is a marker of the theory's boundary. In other areas of physics, when a theory predicts nonsensical results, we don't take those predictions literally. If Newtonian gravity predicts that two masses attract with infinite force when they touch, we don't conclude that infinite forces exist in nature. We conclude that Newtonian gravity is not the right framework to use when objects are in contact. Other forces, electromagnetic and quantum mechanical, take over and prevent the infinite force from manifesting. The same reasoning should apply to singularities. When general relativity predicts infinite curvature, we shouldn't conclude that infinite curvature exists. We should conclude that general relativity is not the right framework to use in that regime. A more complete theory, one that includes quantum effects, should take over and prevent the infinity from arising. This is not just hopeful speculation. We have strong theoretical reasons to believe that quantum effects will resolve singularities. In quantum mechanics, there's a fundamental fuzziness to the concept of position and momentum. The more precisely you try to localize a particle, the more uncertain its momentum becomes. This uncertainty introduces an effective resistance to compression. You can't squeeze something down to an infinitely small point without giving it infinite energy. And while general relativity allows for singular points, quantum mechanics does not. The wave function of a particle, which describes its quantum state, is always spread out over some region, never confined to a point. Similarly, if spacetime is fundamentally quantum, then there should be a minimum meaningful length scale, likely the Planck length. Below that scale, the concept of a smooth, continuous spacetime doesn't make sense. Spacetime becomes discrete or fundamentally uncertain. And in a discrete spacetime, you can't have a singularity in the classical sense. The smallest region you can have is 1 Planck volume. You can't go to 0 volume. This idea is implemented in different ways in various approaches to quantum gravity. In loop quantum gravity, spacetime is quantized. Area and volume come in discrete units. There's a smallest possible area, about 1 square Planck length, and a smallest possible volume, about 1 cubic Planck length. In such a theory, the notion of a zero-volume singularity is nonsensical. The collapse cannot proceed past the Planck scale. Instead, quantum gravitational effects create a repulsive force that halts the collapse and may even cause a bounce, where the collapsing matter rebounds outward. In string theory, the fundamental objects are not point particles, but extended one-dimensional strings. Strings have a characteristic size, the string length, which is also around the Planck length. When matter collapses in string theory, it doesn't form a point-like singularity. Instead, the collapsing mass gets distributed among a huge number of string microstates. The idea is that what looks like a black hole from far away is actually a fuzzball, a dense tangle of strings with no singularity at the center, and, in some versions, no traditional event horizon either. The fuzzball has a size comparable to the would-be event horizon, and it's made of strings in highly excited quantum states. These are different approaches, and they're still being developed and debated. But they share a common theme. Quantum mechanics, when properly incorporated into the description of gravity, removes the singularity. The infinity predicted by classical general relativity is replaced by something finite and, in principle, calculable. The fact that infinities signal a problem doesn't mean the theory is wrong. General relativity is an extraordinarily successful theory. It's been tested extensively and has passed every test in its regime of validity. But no theory in physics is expected to be valid everywhere, at all scales, under all conditions. Newtonian mechanics is not wrong. It's approximately correct in a certain regime. Special relativity extends that regime. General relativity extends it further. And someday, a theory of quantum gravity will extend it beyond even general relativity's reach. The singularity is where general relativity admits its limits. It's where the theory says, "Here, I cannot go." And in that admission, there's a kind of honesty. The infinities are not failures of the theory, but signals pointing toward new physics. They tell us that there's more to learn, deeper layers of reality to uncover. And that, in the end, is a profound message. The universe is subtle. Our current understanding, as impressive as it is not the final word. There are mysteries yet to explore, questions yet to answer. And the singularity, or rather the absence of a singularity, is one of them, the quantum challenge. Now we arrive at the heart of the matter, the place where two of humanity's greatest intellectual achievements stand in tension, unable to be reconciled within our current frameworks. On one hand, we have general relativity, Einstein's geometric theory of gravity, which describes spacetime as a dynamical entity shaped by matter and energy. On the other hand, we have quantum mechanics, the theory governing the behavior of matter and energy at the smallest scales, where uncertainty and probability reign supreme. Each theory is astoundingly successful in its own domain. Yet, when we try to bring them together, To apply both simultaneously to the same situation, we encounter deep and troubling contradictions. Black holes are the ultimate proving ground for this conflict. They're massive enough that gravity, and thus general relativity, is essential to their description. But at their centers, where singularities supposedly lurk, densities and curvatures become so extreme that quantum effects should be unavoidable. We need a theory that incorporates both the large-scale geometry of general relativity and the small-scale quantum behavior of matter and spacetime. We need quantum gravity. But what exactly is the problem with combining quantum mechanics and general relativity? Why can't we simply apply quantum mechanics to the gravitational field in the same way we apply it to electromagnetic fields or nuclear forces? The answer lies in the fundamental differences between how the two theories conceptualize space, time, and reality itself. Quantum mechanics, in its standard formulation, assumes a fixed background of spacetime. There's a stage, a pre-existing arena of space and time, and on that stage, particles and fields perform their quantum dance. The wave function of a particle evolves according to the Schrödinger equation, which tells you how the probability of finding the particle in various states changes over time. But this equation presupposes that time is a well-defined parameter, an independent variable ticking away uniformly in the background. The position of the particle is measured relative to a fixed coordinate system in space. Space and time are not participants in the quantum dynamics. They're the backdrop against which the dynamics occur. General relativity, in contrast, makes space and time themselves dynamical. There's no fixed stage. The geometry of space-time is determined by the distribution of matter and energy, and that geometry, in turn, influences how matter and energy move. Space-time and matter are locked in a dance of mutual influence. Change the matter distribution, and you change the geometry. Change the geometry, and you change how matter moves. Time, in general relativity, is not a universal parameter, but a coordinate that can be chosen in many different ways. The rate at which time flows can vary from place to place depending on the gravitational field. An observer near a black hole experiences time differently from someone far away. When you try to make gravity quantum, you face an immediate conceptual challenge. What plays the role of the fixed background that quantum mechanics requires? If space-time itself is quantum, if it fluctuates and exists in superpositions of different geometries, then there's no stable backdrop against which to define the wave function. The very notion of position and time, which are essential to standard quantum mechanics, become uncertain. One approach is to try to quantize gravity in the same way we've quantized other forces. In quantum electrodynamics, the theory of light and charged particles, the electromagnetic field itself becomes a quantum object. Photons are the quantized excitations of the electromagnetic field. Similarly, we might imagine that gravitons, hypothetical particles of the gravitational field, are the quantized excitations of spacetime. In this picture, gravity would be mediated by the exchange of gravitons, just as the electromagnetic force is mediated by the exchange of photons. This approach works up to a point. You can write down a quantum field theory of gravitons and use it to calculate simple processes, like the scattering of two particles via gravitational interactions. At low energies, these calculations agree with the predictions of classical general relativity. But when you try to calculate processes involving high energies or short distances, the theory breaks down. Infinities appear in the calculations, and unlike in quantum electrodynamics, These infinities can't be removed by renormalization. The theory is said to be non-renormalizable. Each time you try to remove one infinity, new ones appear, and you need to add more and more parameters to absorb them. The theory loses predictive power. It becomes a mess. This non-renormalizability is a technical problem, but it points to a deeper issue. It suggests that treating gravity as just another quantum field in a fixed spacetime. Background doesn't capture the essential physics. Gravity is different from other forces because it's tied to the very structure of spacetime. You can't separate the two. Any successful quantum theory of gravity must account for the fact that spacetime geometry itself is quantum mechanical. Various approaches attempt to address this. String theory posits that the fundamental constituents of nature are not point particles, but tiny, vibrating strings. These strings exist in a higher dimensional spacetime, typically 10 or 11 dimensions, most of which are compactified, curled up so small that we don't notice them. In string theory, gravity emerges naturally from the vibrational modes of the strings. One particular mode corresponds to the graviton. The theory is finite and avoids the infinities that plague point-particle theories of gravity. Moreover, it includes all the other forces, unifying gravity with electromagnetism and the nuclear forces in a single framework. But string theory is complicated and remains incomplete in many ways. It predicts a vast landscape of possible vacuum states, different ways the extra dimensions could be compactified, each leading to a different set of physical laws and constants in our observable four-dimensional universe. We don't know which of these possibilities, if any, corresponds to our universe. And direct experimental tests of string theory are challenging because the strings are so small, near the Planck scale, far beyond the reach of current particle accelerators. Loop quantum gravity takes a different approach. Instead of starting with strings in a higher dimensional spacetime, it attempts to quantize general relativity directly. The theory treats spacetime as a network of discrete loops, a spin network, where geometric quantities like area and volume are quantized. There's a smallest possible area and a smallest possible volume, both on the order of the Planck scale. In loop quantum gravity, the smooth continuum of classical spacetime emerges as an approximation, valid at large scales, of an underlying discrete quantum structure. One of the most exciting results from loop quantum gravity is the resolution of singularities. In classical general relativity, a collapsing star forms a singularity at its center. In loop quantum gravity, the quantum structure of spacetime prevents this. As matter collapses and the curvature increases, quantum gravitational effects become strong. These effects create a repulsive force that halts the collapse. The matter doesn't reach infinite density. Instead, it reaches a maximum density, on the order of the Planck density, and then bounces back. Some versions of the theory suggest that this bounce could connect the interior of a black hole to the interior of a white hole, a hypothetical object that is the time reverse of a black hole, ejecting matter instead of swallowing it. Both string theory and loop quantum gravity are works in progress. Neither has been experimentally confirmed, and both face significant theoretical challenges. But they offer glimpses of how quantum mechanics and general relativity might be reconciled. And in both approaches, the classical singularity disappears. The infinities that general relativity predicts are replaced by finite, albeit extreme, quantum states. Another key issue in quantum gravity is the question of time. In general relativity, time is part of the dynamical geometry. There's no universal clock ticking away in the background. Different observers can slice spacetime into space and time in different ways, and all are equally valid. But in quantum mechanics, time plays a special role. It's the parameter in the Schrödinger equation that governs evolution. The wave function at one time determines the wave function at later times. Time is external to the system, a backdrop. In canonical quantum gravity, an approach closely related to loop quantum gravity. This tension is encoded in what's called the Wheeler-DeWitt equation. This equation describes the quantum state of the entire universe, including its geometry. But remarkably, the equation has no explicit time variable. It describes a timeless state. This is known as the problem of time. If the quantum state of the universe is timeless, how do we recover the sense of time passing that we experience? How do we describe change and evolution? Various proposals have been made. One idea is that time is an emergent concept, arising from correlations within the quantum state. Another is that we need to treat time as we treat other dynamical variables, allowing it to fluctuate quantum mechanically. There's no consensus yet on the right way to handle time in quantum gravity, but the problem highlights just how profound the conceptual shifts required might be. The Planck scale itself is a clue to the unification of quantum mechanics and gravity. The Planck length is derived from fundamental constants, the gravitational constant, which measures the strength of gravity, Planck's constant, which sets the scale of quantum effects, and the speed of light, which connects space and time. Combining these constants gives you a length, the Planck length, about 1.6 times 10 to the minus 35 meters. At this scale, the quantum fluctuations of spacetime become comparable to the spacetime curvature itself. You can't ignore quantum effects on gravity, and you can't ignore gravitational effects on quantum mechanics. Everything is entangled. At the Planck scale, our intuitions about space and time likely break down completely. Space might not be a smooth continuum, but a foamy, fluctuating structure. Time might not flow uniformly, but branch and merge in complex ways. Causality, the idea that causes precede effects, might be fundamentally ambiguous. These are speculations, but they're grounded in the mathematics of quantum gravity and the need to reconcile quantum mechanics with general relativity. What does all this mean for black holes and singularities? It means that as matter collapses past the event horizon and approaches the region where the singularity would classically form, quantum effects become dominant. The classical equations of general relativity cease to apply. The geometry of spacetime becomes uncertain, subject to quantum fluctuations. The collapsing matter doesn't reach a point of infinite density. Instead, it enters a quantum regime where the concepts of position, density, and curvature must be radically rethought. Different quantum gravity theories give different detailed pictures, but they share common themes. The singularity is replaced by a quantum core, or a quantum bounce, or a tangle of strings, or some other finite, structured quantum state. The infinities vanish. The laws of physics remain well defined, even if those laws are not yet fully understood. The challenge of quantum gravity is one of the deepest in all of physics. It's a problem that has occupied some of the brightest minds for decades, and it remains unsolved. We don't have a complete, experimentally tested theory of quantum gravity. We have candidate theories, frameworks that show promise but also face obstacles. And we have clues, hints from the mathematics and from thought experiments that point toward a resolution. But the absence of a final answer doesn't mean we should default to the classical picture. Just because we don't yet have quantum gravity doesn't mean the singularity is real. The weight of theoretical evidence strongly suggests that the singularity is an artifact, a place where general relativity, a classical theory, breaks down. Quantum mechanics must play a role, and when it does, the infinity goes away. In the quiet moments of contemplation, when we think about the nature of reality at its most extreme, it's comforting to remember that the universe doesn't owe us easy answers. The fact that we don't fully understand quantum gravity is not a failure. It's an invitation. It's the frontier, the edge of human knowledge, the place where the next great discoveries await. And those discoveries will almost certainly show that the singularity is not the end of the story. It's the beginning of a new chapter, one written in the language of quantum geometry and spacetime foam, a chapter we're only just starting to read. Proposed solutions. Loop quantum gravity. Let's explore one of the most promising approaches to quantum gravity in more detail, a framework called loop quantum gravity. This theory takes a bold and direct approach. It attempts to quantize general relativity itself without introducing new entities like strings or extra dimensions. The result is a picture of spacetime that is fundamentally discrete, granular, and quantum mechanical at the smallest scales. And, crucially, in this picture, the classical singularity simply cannot exist. Loop quantum gravity, often abbreviated as LQG, has its roots in the canonical quantization approach to general relativity. In the 1980s, physicists Abhay Ashtekar, Lee Smolin, Carlo Rovelli, and others developed a reformulation of general relativity that made it more amenable to quantization. They introduced new variables, now known as Ashtekar variables, that describe the gravitational field in a way that looks more like the gauge theories used to describe other fundamental forces. The key insight was to focus on loops, closed curves in space, and calculate how the geometry of spacetime affects parallel transport around these loops. In general relativity, when you parallel transport a vector around a closed loop in curved space, it comes back rotated. The amount of rotation tells you about the curvature of space along that loop. By considering networks of intersecting loops, you can encode information about the entire geometry of space. These networks are called spin networks. When you quantize the theory, these spin networks become the fundamental entities. Spacetime is not a smooth continuum, but a quantum superposition of different spin network states. Each spin network represents a particular configuration of quantum geometry. The links in the network carry quantum numbers that determine how much area and volume they contribute. Remarkably, when you calculate the spectrum of these geometric operators, you find that area and volume are quantized. They come in discrete units, multiples of the Planck area and Planck volume. This is a profound result. It means there's a minimum possible area in nature, about 1 square Planck length, and a minimum possible volume, about 1 cubic Planck length. You cannot have regions of space smaller than this. The smooth, infinitely divisible space of classical geometry is an illusion, an approximation that works at large scales but breaks down at the Planck scale. At the fundamental level, space is granular. What does this mean for black holes and singularities? In classical general relativity, a collapsing star can shrink to a point of zero volume and infinite density. But in loop quantum gravity, there's a minimum volume. The collapse cannot proceed past the Planck scale. As the matter density increases and approaches the Planck density, quantum gravitational effects become strong. The discrete structure of spacetime resists further compression. The geometry itself pushes back. One of the most studied scenarios is the collapse of a homogeneous dust cloud, a simplified model of a collapsing star. In classical general relativity, this collapse inevitably leads to a singularity. But when the same scenario is analyzed using loop quantum cosmology, which applies the techniques of loop quantum gravity to cosmological settings, something different happens. The collapse reaches a maximum density and then bounces. The matter rebounds outward in an expansion phase. This quantum bounce is not due to any new form of matter or exotic pressure. It's a consequence of the quantum geometry of spacetime. The discrete nature of space, combined with the uncertainty principle, creates an effective repulsive force at Planck scale densities. This force halts the collapse and reverses it. In the context of a black hole, this bounce suggests a fascinating possibility. The interior of a black hole might not end in a singularity, but transition to a white hole, an object that is the time reverse of a black hole. A white hole would be a region from which matter and light can escape, but into which nothing can enter. The bounce would occur in a tiny region near what would classically be the singularity. From outside the event horizon, we wouldn't see any difference. The black hole would still appear as a dark shadow swallowing light and matter. But inside, the story is different. Matter falling past the horizon would eventually reach the Planck density core, bounce, and potentially emerge in another region of space-time or even another universe. This is highly speculative, and there are many open questions. How long does the bounce take? What happens to the information carried by infalling matter? Does the transition from black hole to white hole occur quickly or over a vast timescale? These are active areas of research, and definitive answers require more complete calculations and a better understanding of how to describe black hole interiors in loop quantum gravity. Another important aspect of loop quantum gravity is its prediction for the entropy of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizon. This Bekenstein-Hawking entropy is a measure of how many microscopic states correspond to a given black hole. It's a profound hint that black holes are not featureless objects, but have internal structure. In loop quantum gravity, the event horizon is not a smooth surface but a quantum geometry pierced by the links of spin networks. Each link that punctures the horizon contributes to its area. By counting the number of ways you can arrange these links to produce a given total area, you can calculate the entropy. Remarkably, loop quantum gravity reproduces the Bekenstein-Hawking formula, with the correct proportionality constant from first principles. This is a major success of the theory and a strong hint that it's capturing something real about the quantum structure of spacetime. However, loop quantum gravity is not without its challenges. One of the biggest is recovering classical general relativity in the appropriate limit. At large scales, far from the Planck length, spacetime appears smooth and continuous. Loop quantum gravity must explain how the smooth geometry emerges from the underlying discrete structure. This is analogous to how a smooth fluid, like water, emerges from the collective behavior of countless discrete molecules. But the mathematics of this limit is complex, and it's not yet fully understood how to recover all the features of general relativity from loop quantum gravity. Another challenge is coupling matter to the quantum geometry. In general relativity, matter and geometry interact intimately. Matter curves spacetime, and the curvature affects how matter moves. In loop quantum gravity, we need to describe how matter fields, represented quantum mechanically, interact with the discrete quantum geometry. Progress has been made, but a complete formulation remains a work in progress. Despite these challenges, loop quantum gravity offers a compelling vision of quantum spacetime. It's a theory that takes general relativity seriously and attempts to extend it into the quantum realm without abandoning its core insights. And it provides a concrete mechanism for resolving singularities. The granular structure of space itself prevents infinite densities from forming. The picture that emerges from loop quantum gravity is one where space-time, at the deepest level, is a web of quantum relations, a network of connections that weaves together to create the illusion of smooth, continuous geometry. At the Planck scale, this web is visible. Space is not empty but filled with quantum geometric degrees of freedom. And when matter collapses, it doesn't vanish into a point of nothingness. It encounters the fundamental graininess of space and bounces back. The singularity in this framework is replaced by a Planck scale core, a region of extreme but finite density and curvature where quantum geometry dominates. It's a region we cannot access with classical physics, but it's not a breakdown of physics. It's physics at its most fundamental, operating at the edge of space and time as we understand them. This is one way the quantum nature of reality might save us from the infinities predicted by classical theory. It's a beautiful example of how deeper understanding often comes from taking bold steps, from questioning assumptions that seem unshakable. The assumption that space is smooth and continuous seems so obvious, so fundamental. But loop quantum gravity suggests it's wrong. And in that wrongness lies the key to resolving the singularity, the information paradox connection. Before we drift further into the night, we should talk about one more profound puzzle related to black holes, a puzzle that has captivated physicists for decades and is intimately connected to the question of singularities. This is the black hole information paradox, a conundrum that arises when we consider the fate of information that falls into a black hole. And the resolution of this paradox, like the resolution of the singularity problem, requires quantum mechanics to be taken seriously at the scale of event horizons and black hole interiors. In the 1970s, Stephen Hawking made a remarkable discovery. By applying the principles of quantum field theory to the curved spacetime around a black hole, he showed that black holes are not entirely black. They emit radiation. This phenomenon, now known as Hawking radiation, arises from quantum fluctuations near the event horizon. Particle-antiparticle pairs spontaneously pop into existence from the vacuum. Normally, they annihilate almost immediately, but near the horizon, one member of the pair can fall into the black hole while the other escapes. To a distant observer, the escaping particles look like thermal radiation coming from the black hole. The temperature of this radiation is tiny for large black holes, inversely proportional to their mass. For a solar mass black hole, the temperature is about 1/millionth of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. Such a black hole would absorb more radiation than it emits and grow over time. But for very small black holes, the temperature is higher. And, crucially, as a black hole emits radiation, it loses mass. The more it radiates, the lighter it gets, and the hotter it becomes, accelerating the radiation process. Eventually, the black hole evaporates entirely, disappearing in a final burst of energy. This discovery was revolutionary. It linked black holes to thermodynamics in a deep way. Black holes have temperature. They have entropy. They can evaporate. But it also led to a paradox. In quantum mechanics, information is never destroyed. The state of a quantum system at one time fully determines its state at any later time, provided you know the laws of physics. This is called unitarity. It means that if you know the initial state of the universe in perfect detail, and you have the equations governing how the state evolves, you can, in principle, calculate the state at any future time. And equally, you can work backward and reconstruct the past. Information is conserved. Now imagine throwing a book into a black hole. The book contains information, the arrangement of words on its pages, the sequence of letters, the meaning conveyed by the text. Once the book crosses the event horizon, it falls toward the center and, according to classical general relativity, hits the singularity and is destroyed. But even if there's no classical singularity, the book is inside the horizon, hidden from the outside world. Now, the black hole evaporates via Hawking radiation. Hawking's original calculation suggested that this radiation is purely thermal, carrying no information about what fell into the black hole. It's like the radiation from a hot coal, which depends only on temperature, not on what you burned to make the coal hot. If the radiation is truly thermal, then once the black hole evaporates completely, all that's left is a random gas of particles. The information about the book, about what fell in, is gone. But this violates unitarity. Information has been destroyed. The initial state, which included a book, cannot be reconstructed from the final state, which is just featureless radiation. This is the information paradox. For many years, physicists debated the resolution. Hawking initially believed that information was indeed lost, that black hole evaporation was an exception to the rules of quantum mechanics. Others, including many quantum theorists, argued that information must be preserved, that there had to be subtle correlations in the Hawking radiation that carry information about what fell in, even if those correlations are extremely difficult to detect. The debate was partly settled by theoretical work in string theory and ADS/CFT correspondence, which strongly suggests that information is preserved. In the holographic dual of a black hole, the evaporation process is described by a unitary quantum field theory. Information is not lost. It's encoded in subtle correlations in the radiation. More recently, calculations involving quantum extremal surfaces and the so-called islands in black hole spacetime have shown that even in semi-classical gravity, which doesn't require a full quantum gravity theory, you can get results consistent with unitarity. The entropy of Hawking radiation initially increases as the black hole evaporates, but then, after about half the black hole's mass has been radiated away, it starts to decrease. This behavior, called the Page curve after Don Page, who predicted it, is exactly what you'd expect if information is being preserved and returned to the outside world. These calculations are complex and rely on some deep and not yet fully understood aspects of quantum gravity. But they point in a consistent direction. Information is not lost. The Hawking radiation, when properly accounted for with quantum gravity effects, does carry information about what fell into the black hole. Now, how does this connect to the singularity? One answer is that if there's no singularity, If the interior of the black hole is described by quantum gravity, then information can be stored in the quantum state of the black hole's interior. In the fuzzball picture, the information is in the quantum state of the strings. In loop quantum gravity, it might be in the quantum state of the spacetime geometry itself. If there were a true singularity, a place where physics breaks down completely, it's hard to see how information could be preserved. The singularity would be a place where things cease to exist in any meaningful sense, where time ends, where the laws of physics no longer apply. Information falling into such a region would seemingly be destroyed. But if the singularity is replaced by a quantum core, a structured quantum state governed by well-defined, albeit unknown, laws of quantum gravity, then information can be stored and potentially recovered. The resolution of the information paradox and the resolution of the singularity problem are two sides of the same coin. Both require us to abandon the classical picture of black hole interiors and embrace a quantum description. Both point to the need for a complete theory of quantum gravity. And both suggest that the infinities and breakdowns predicted by classical general relativity are not physical realities, but signs that we need a better framework. It's worth reflecting on how remarkable this is. Black holes, those most extreme and enigmatic objects in the cosmos, have become laboratories for testing the deepest principles of physics. They sit at the intersection of gravity and quantum mechanics, forcing us to confront the limits of our current theories and pushing us toward a more complete understanding of nature. The singularity paradox and the information paradox are not separate problems. They're facets of the same underlying mystery. And their resolution will require a synthesis of the two great pillars of 20th century physics: general relativity and quantum mechanics. As you lie here, letting these ideas wash over you, you might feel a sense of awe at the sheer ambition of it all. Physicists are trying to understand what happens at the centers of black holes, regions we can never observe directly, using theories that describe phenomena at scales billions of times smaller than an atom. We're probing the nature of space and time themselves, asking whether they're fundamental or emergent, continuous or discrete, deterministic or probabilistic. And we're doing this not through wishful thinking or philosophical speculation, but through rigorous mathematics, careful reasoning, and a deep respect for empirical evidence and logical consistency. The answers are not yet in hand, but the questions are clear, and the journey toward those answers is one of the great intellectual adventures of our time. What probably exists instead? So, if the singularity is not real, what takes its place? What lies at the heart of a black hole, hidden behind the event horizon, in that region where classical general relativity predicts infinite curvature and density? We've discussed various theoretical frameworks: loop quantum gravity, string theory, each with its own answer. But can we say anything more concrete? Anything that captures a consensus view among physicists working on these problems? The answer is yes, to some extent. While the details depend on the specific theory, there are common themes, features that appear in multiple approaches and seem likely to be part of the correct description, whatever that turns out to be. First, at the center of a black hole, there is almost certainly a region where quantum gravitational effects dominate. This region has a size on the order of the Planck length, or perhaps a bit larger depending on the mass of the black hole and the specifics of the quantum gravity theory. In this region, spacetime is not a smooth continuum but a quantum object, subject to fluctuations and uncertainty. The geometry is not well defined in the classical sense. Concepts like distance and curvature become fuzzy, probabilistic, In loop quantum gravity, this region is described by a spin network, a discrete quantum geometry. The area and volume are quantized, coming in discrete units. As matter collapses and reaches this region, it cannot compress further. The discrete structure of spacetime resists. Quantum gravitational effects create an effective repulsive force, halting the collapse. The matter reaches a maximum density, the Planck density, about 10 to the 96 kilograms per cubic meter, an unimaginably enormous but finite value. What happens next is still debated. Some models suggest a quantum bounce, where the matter rebounds and potentially emerges as a white hole, a time-reversed black hole that expels matter. This bounce would occur very quickly on the scale of the Planck time, about 10 to the minus 43 seconds. But from the perspective of a distant observer, due to the extreme time dilation near the black hole's center, this rapid bounce might correspond to vast eons of external time. In string theory, the region is filled with strings in highly excited quantum states. These strings form the fuzzball, a dense tangle of quantum matter. There's no singularity, no empty interior, no point where density diverges. Instead, the mass of the black hole is distributed throughout the fuzzball in a complex quantum state. The fuzzball has a size roughly equal to the classical Schwarzschild radius, so from the outside, it looks like a black hole with an event horizon. But the horizon is not a sharp boundary, but a fuzzy transition region where the density of strings drops off. Another proposal, which appears in several contexts, is the Planck star. This is a hypothetical object where the collapse of matter is halted by quantum gravitational effects right at the Planck scale. The resulting object is a kind of ultra-dense core, a remnant of the collapsed star, supported not by electron degeneracy pressure or neutron degeneracy pressure, but by the quantum structure of spacetime itself. From the outside, a Planck star would be indistinguishable from a classical black hole. It would have an event horizon, strong gravity, the works. But inside, there's a tiny, incredibly dense quantum object, not a singularity. Some variants of the Planck star idea suggest that this object could eventually explode, converting its mass back into radiation in a kind of quantum gravitational phase transition. This would be a far future event, potentially taking vast amounts of time, far longer than the current age of the universe. But in principle, a Planck star could evaporate not only through Hawking radiation, but through this internal quantum process. All these pictures share common elements. The singularity is replaced by a finite, structured quantum core. The laws of physics remain well defined, even if those laws are quantum gravitational and beyond our current understanding. And information is preserved, encoded in the quantum state of the core. Another important point is that these quantum cores are small. For a stellar mass black hole, the event horizon has a radius of a few kilometers. But the quantum core, the region where quantum gravity effects are strong, is only about the Planck length in size. That's 10 to the minus 35 meters, smaller than the smallest atom by a factor of a billion. So, the vast majority of the black hole's interior, the region between the horizon and the core, is still described reasonably well by classical general relativity. It's only in the tiniest region at the very center that quantum gravity takes over. This means that an observer falling into a black hole wouldn't notice anything strange until they got very, very close to the center. They'd cross the event horizon, perhaps without even realizing it if the black hole were large enough. They'd continue falling inward through a region where spacetime is curved, but still classical. Only at the very end, when they approached the quantum core, would they encounter the true quantum gravitational realm. And at that point, our ability to predict what they'd experience breaks down, not because physics breaks down, but because we don't yet have the full theory. It's also worth noting that for supermassive black holes, the ones at the centers of galaxies with masses of millions or billions of suns, the quantum core is still Planck scale in size. But the event horizon is enormous, perhaps billions of kilometers across. The ratio of the core size to the horizon size is mind-bogglingly small. This means that for all practical purposes, the classical description of spacetime applies almost everywhere inside the black hole. The quantum region is a tiny speck at the center, insignificant compared to the vast interior. Yet that tiny speck is where the resolution of the singularity lies. It's where the infinities of classical theory are replaced by the finite, structured quantum physics. And it's where the information that falls into the black hole is ultimately stored and potentially recovered. There's a beautiful irony here. The most extreme objects in the universe, black holes, with their immense gravity and their ability to warp spacetime beyond recognition, are governed in their deepest interiors by the smallest scales in nature. The Planck scale, the realm of quantum gravity. The macroscopic and the microscopic meet at the heart of a black hole. The cosmic and the quantum are intertwined. This should give us a sense of the unity of physics. The same fundamental laws that govern the behavior of subatomic particles in laboratories on Earth also govern the cores of black holes billions of light years away. The universe is not a collection of disconnected phenomena, but a single coherent whole, described by a single set of laws. We don't yet know all those laws. Quantum gravity is still a mystery. But the connections are there, waiting to be uncovered. So, what is at the heart of a black hole? Not a singularity, not a point of infinite density where physics ends, but a quantum core, a region of extreme but finite density and curvature, governed by quantum gravity, a region where spacetime is no longer smooth but discrete, quantum, uncertain, a region where information is preserved, where the laws of nature remain intact, where the universe, in all its quantum strangeness, continues to operate in ways we're only beginning to fathom. And the fact that we can't yet describe this region with precision, that we don't have a complete theory of quantum gravity to tell us exactly what's happening, doesn't diminish the achievement. It highlights it. We've pushed our understanding to the very edge of what's knowable with current theories. We've identified the place where new physics must emerge, and we've laid the groundwork through decades of theoretical work for the next generation of physicists to take the final steps. The singularity is not the end. It's a doorway, a threshold, an invitation to go deeper. And on the other side, there's not nothing, not a breakdown of reality, but something rich and structured and deeply quantum. Something we're learning to describe, one equation at a time, one insight at a time, one step further into the unknown. Closing. As we come to the end of this journey through the darkness and the light, through the curves of space-time and the granularity of quantum geometry, let's take a moment to rest in the quiet satisfaction of questions asked, even if not fully answered. We've traveled from the observable certainty of black holes, those shadows against the cosmic backdrop, to the uncertain heart where general relativity falters, and quantum mechanics must take the stage. We've seen that the black hole is real. The evidence is overwhelming. We've detected gravitational waves from merging black holes. We've photographed the glowing rings around their event horizons. We've tracked stars orbiting invisible masses at the centers of galaxies, masses so compact and dense they can only be black holes. These objects exist. They shape the evolution of galaxies. They mark the final fate of the most massive stars. They are woven into the fabric of the cosmos. But the singularity, that point of infinite density, predicted by general relativity, is almost certainly not real. It's a mathematical artifact, a place where the equations break down because they're being applied beyond their domain of validity. General relativity is a classical theory, and, at the extreme conditions found at a black hole's center, quantum effects cannot be ignored. When we account for quantum mechanics, when we move toward a theory of quantum gravity, the infinity vanishes. The singularity is replaced by something finite, a quantum core, a Planck star, a fuzzball of strings, a discrete quantum geometry. The details depend on the approach, but the common theme is clear. Physics doesn't end at the heart of a black hole. It transforms. This is a profound lesson, not just about black holes, but about the nature of science itself. Our theories are not eternal truths handed down from on high. They're tools, frameworks we construct to make sense of the universe. And, like any tool, they have limits. Newtonian mechanics works beautifully for apples falling from trees and planets orbiting stars, but it fails for objects moving near the speed of light. Special relativity extends the reach, but it can't handle gravity. General relativity handles gravity, but it breaks down in the quantum realm. Each theory is a stepping stone, a way station on the path toward deeper understanding. The fact that general relativity predicts singularities doesn't mean it's wrong. It means it's incomplete. It's pointing us toward something more, a theory that encompasses both the smooth geometry of spacetime and the quantum graininess of matter and energy. We don't have that theory yet, not in finished form. But we have clues. We have loop quantum gravity, string theory, and other approaches, each offering glimpses of the final picture. And in the meantime, we have the humility to say, we don't know. We don't know exactly what's at the center of a black hole. We don't know the precise equations of quantum gravity. We don't know if spacetime is fundamentally discrete or emergent or something else entirely. But we know enough to say that the singularity, as classically conceived, is not the answer. The universe doesn't end in infinities. It continues in forms we're still learning to describe. There's a kind of peace in this uncertainty, a comfort in the knowledge that reality is richer than our current understanding. The universe isn't obligated to make sense to us. It doesn't owe us easy answers or intuitive pictures. And yet, through patience and rigor and creativity, we've managed to peel back layer after layer of the mystery. We've gone from wondering if black holes exist to imaging their shadows. We've gone from treating space-time as an absolute background to understanding it as a dynamical entity. We've gone from seeing particles as fundamental to envisioning them as vibrations of strings or excitations of quantum fields. Each step forward has been hard-won, the result of brilliant minds grappling with profound questions, making mistakes, debating fiercely, and gradually converging on deeper truths. And the journey is far from over. Quantum gravity remains the holy grail, the ultimate unification of our two best theories. When we finally achieve it, when we can describe the Planck scale with the same confidence we describe the macroscopic world, the secrets of black holes will be laid bare. The singularity will be fully understood as the placeholder it is, and we'll know what truly lies at the heart of these cosmic giants. But until then, we have the wonder, the thrill of standing at the edge of knowledge, peering into the unknown. The satisfaction of understanding that even our ignorance is structured, informed by what we do know. We may not have quantum gravity, but we know it must resolve the singularities. We may not know the exact quantum state of a black hole's interior, but we know it's finite and governed by laws, even if those laws are still being written. So, as you drift toward sleep, as the weight of the day settles and the boundaries of consciousness soften, take comfort in the grand tapestry of knowledge and mystery. The universe is vast, ancient, and strange beyond measure. Black holes are real, monuments to gravity's power, final resting places for matter compressed beyond recognition. But they're not ends. They're transitions, gateways, places where one set of rules gives way to another. And the singularity, that troubling infinity at the heart of the classical picture, is not a wall but a window. Through it, we glimpse the quantum nature of spacetime, the granular foundation of reality, the deep unity of the forces and fields that make up everything we see. The black hole is real, but the singularity is not. And in that simple statement lies a universe of understanding, hard-won and beautiful, a testament to the human drive to comprehend the cosmos and our place within it. Rest now. Let these thoughts settle like dust after a storm. The universe will still be here tomorrow, vast and mysterious, waiting for the next question, the next insight, the next step forward into the light. Thank you for joining me on this journey through the Science Pillow. Sleep well, and may your dreams be as vast and wondrous as the cosmos itself.